Here's some homework help for 6.1, day 2, page 301, and here is number 24. So you take 325 milligram dosage of ibuprofen. During each subsequent hour, the amount of medication in your bloodstream decreases by about 29% each hour. So we're going to write an exponential decay model, giving the amount in milligrams of ibuprofen in your bloodstream t hours after the initial dose. So we know it's decay. We're looking at y equals a times 1 minus r raised to the t. And so they say it decreases by 29% each hour. So A equals 325, R equals 0.29. So it was 29%, and you convert that. So now we plug it in. Y equals 325 times 1 minus the R, 0.29 raised to the t. And so when you subtract 1 minus 0.29, that is 0.71 raised to the t. And so that is the equation, okay? Then estimate how long it takes for you to have 100 milligrams of ibuprofen in your bloodstream. So in this answer, you have to plug it into Desmos, right? So you plug this equation into Desmos. And then after that, you plug in y equals 100. And when you do that, you'll find that x value. So if you click on that, you'll see where it intersects the graph at some point, so at 100. And then so it'll be something of 100, and that x value is what it is, and it's about 3 hours. Okay, it's about 3 hours. Let's look at number 27. When a plant or animal dies, it stops acquiring carbon-14 from the atmosphere. The amount y in grams of carbon-14 in the body of an organism after 2 years is given by this equation, where A is the initial amount in grams. We want to find the percent of the carbon-14 that is released each year. So we're looking at decay that's less than 1. So y equals A times 1 minus r raised to the t. So in order to do this, we have to evaluate what we have. So let's separate it out. Y equals A, and then times 0.5, and then we're going to raise it to the 1 over 5,730, and then the t is on the outside. So we want to evaluate what we have before we can find r. So this you plug into the calculator. As a reminder, you plug in 0.5 and then the caret or the y to the x button, depending what calculator you're using, and then parentheses, 1 divided by the 5,730, close parentheses, and then equal. And then you want to round to 4 decimal places. And don't forget to bump it up if it's high. Now, looking at this example, after you plug it in, you will find that that value, after you plug this in the calculator, is about 0.9999. I'm going to keep it like that. It's raised to the t. Now, this is decay. So remember, in order to find r, right, this is the number inside, 1 minus r. Remember, in the general exponential equation, y equals a b to the x, that this b is 1 minus r. So currently b is this number, so b equals 1 minus r. So in order to solve for r, we do 0.999 equals 1 minus r, and then we solve for r. So subtract 1 from both sides. We find that's negative 0.00012 equals negative r. Divide by a negative 1. You would find you would get 0.00012 equals r, multiply by 100, and then so you find that the rate is 0.012% in this case. Let's try number 28. The number y of duckweed fronds in a pond after t days is given by this equation, where a is the initial amount number of fronds. By what percent does the duckweed increase each day? So we're looking at y equals a times 1 plus r raised to the t. You see it's greater than 1, so that should make sense. So now we want to separate this 1 over 16 here. So let's write it 1,230.25, and it's raised to the 1 over 16, and then t is on the outside. So we're again using the power of a power property. Then you could plug this in your calculator, right? We can't find r without plugging that in. So then when you plug it in, that you will get 1.560 raised to the t. So you have to round it, and then you'll get this value. Then remember you set this piece equal to the 1 plus r. 1.560 equals 1 plus r, subtract 1. So notice we're always subtracting 1 every single time, and it's after you evaluate with the calculator. So you get r is 0.560, you multiply by 100, and so you notice that the growth rate is 56.0% growth.